Okay, so now we want to consider what happens if I open this system up to mass flow. How does that change my equation? So I still have my system and I still have my surroundings, but now I'm going to add an inlet stream and an outlet stream. And these could be arbitrary in number. I can have as many inlet streams as I want, as many outlet streams as I want. So we'll call this flowing in at some mass flow rate J, this flowing out at some mass flow rate J, and I can add some amount of heat, add or remove some amount of heat to the system Q. I can add or remove some amount of work from this system W. So what I want to do is I want to develop what the energy balance for a system like this needs to look like. So I know that is going to be the heat that I add or remove to the system, right, plus the work that I add or remove to the system, plus the sum over all of the inlet streams of the total energy carried by those streams in, and that has to equal the sum of all the streams leaving of all of the energy going with those streams leaving. All right, so this hopefully intuitively makes sense. The change in energy of the system is going to be equal to all the heat or work I add or subtract, plus all of the energy carried in and out by the streams entering or leaving. So the energy of a stream, right, what is the energy of a stream made up of, right? So energy of a stream. Well, it's going to be made up of the stream's internal energy, right? The stream is going to be composed of molecules that have a certain amount of internal energy assigned to them, right? It's also going to be made up of what we're going to call the macroscopic Ke, right, kinetic energy, right? A mass of fluid moving at a certain velocity has a given kinetic energy, right? And it also is going to be comprised of what we'll call macroscopic potential energy, right? So a massive fluid in a gravitational field at a certain height above or below some reference line is going to have a certain amount of potential energy. So I can therefore write that E sub j, right, is going to be the mass, right, times the, times the specific internal energy per unit mass for the stream, plus Vj squared over 2, right? That's the kinetic energy, plus Gz sub j, right? So this represents the internal energy. Mass times the velocity squared over 2 is the kinetic energy. So this is internal, this is kinetic, and then m times Gz is my potential energy term. Okay? So we're going to keep that in mind as we continue to develop this. Right? The other thing we want to continue to consider is work, right? So my work term, right, work, I'm going to divide into two pieces. I'm going to call one of them shaft work, which is work done by motors or shafts or things in the flow field or in the fluid itself, right? Plus what I'm going to call flow work, and this is work done by or on the fluid, moving it through through the different processes, through the different pipes, right, or things that get it around. So if I consider the flow work for a minute, I have a process here, and I've got, right, V in meters cubed per second, and I've got a pressure in Newton per meter squared. And then I've got on the other side of the process V out, again in cubic meters per second, and a pressure out, right, in newtons per meter squared, right? And so I can say that the work done by the fluid in moving through the process, right, getting it in, W in, right, is P in, V in. And if I look at the units on that, it's going to be newtons per meter squared times meters cubed per second, which if I do it out is Newton meters per second, which is a joule per second, which is a watt, which is a unit of energy per unit time. So that flow rate, that volumetric flow rate times the pressure it's at, gives me a work term, right? So I can do the same thing, for out. And so I can say that my flow work flow, is equal to P in, V in, right, the net work, right, minus P out, V out. And I can also arbitrarily take that to any number of input and output streams, right? So I can say that work flow is equal to the sum of over all the inlet streams of m dot j times pj times the specific volume of stream j, right, minus the sum over the outlet streams of the mass flow rate times the pressure out times the specific volume of stream j. Okay, so this particular equation for flow work is going to be important, right, as is, right, my definition of energy for the streams. Because what I want to do is I want to combine this equation and this equation with the equation up here, right? So I want to substitute in for my definition of work with shaft work and flow work, and I want to substitute in my definition with energy carried by the streams. So if I do all this, right, this is going to be a big equation, I can see that, right, Q, right, Q plus shaft work now, right, because I've broken out flow work, right, plus the sum over all of the inlet streams of m dot j times specific internal energy plus pj vj plus v squared j over 2 plus g zj, right, has to be equal to, right, the sum on the outlet side of mj dot times uj plus pj vj out plus velocity squared of stream j over 2 plus g z, right? And so these two are the same. These two are the same, just inlet and outlet. So something very interesting happens here, because if we look at this, we notice that we have U plus PV in both of these streams. And if you have read the textbook and you have looked at what that is in thermodynamic definitions, right, U plus PV is defined as H, or enthalpy. Right? So enthalpy, right, for a flowing stream includes not only the energy that comes from the material itself, the internal energy, but it also counts for the energy in the flow of the stream, right? So U plus the PV work is how we define enthalpy. So that lets us make a simplification, right? So this we're going to call, right, we're going to combine this and call this H sub j, or the enthalpy of the stream. So if I do a little bit of mathematical simplification and make some definitions, right, I can separate this out. I can say that the sum out over m dot j hj minus the sum in of m dot j hj, we're going to call that basically delta h, right? I can do the similar thing for v squared over 2, right? And that's v squared j over 2, everything being the same. We can call that delta EK, or the change in kinetic energy, right? And I can do the same, right, the same equation for G Z sub J, G Z sub J, right? This is ditto, right? And I can define that as delta EP, right? So if I do all that, right, so combining my definition for flow work, combining my definition for enthalpy, taking into account all the streams that enter and leave, right, what I can say then, right, is that delta H plus delta E sub K plus delta E sub P is equal to Q dot plus WS, right? And this is general, and this is for an open system, right? So for an open system, the energy balance has to take into account all the heat that enters or leaves, all of the shaft work that we do or remove, right? All of the changes in potential energy of the macroscopic fluid flow, all of the changes in kinetic energy of the macroscopic fluid flow, and all of the enthalpy changes of the streams. And what you should be able to see, right, is if I go back up here, right, to the very general form of this equation, right, if I don't have any streams, right, so what happens if I don't have any streams, right? So if none of the streams coming in or out exist anymore, right, that goes away, 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 right? And what I'm left with is delta U is equal to Q plus W, which is my closed system energy balance. So you see the open system energy balance will collapse back to the closed system energy balance if all the streams go away, which is exactly what we should expect, right? And so if I have a system, right, if I have a system, right, without macroscopic changes in kinetic energy or potential energy, i.e. my system is not moving or it's not changing in elevation significantly, right, then this, right, for an open system basically reduces to delta H equals Q dot plus shaft work. And for my closed system, right, the analogy was changes in internal energy was equal to Q plus W, right? So we see that in general, enthalpy is what we use for open systems because it incorporates concepts for flow work, and internal energy is what we use for closed systems because there is no flow work, right? So that is, in a nutshell, how we developed both the open system energy balance and the closed system energy balance in a general sense.